something exiting, and how can you use things like the function or the integral or like the rewritten first FTC to basically do a bunch of different types of problems. Today we are just going to do PVA. I'm not going to do like every single type of PVA problem since we did technically look at that first semester. I'm mainly going to focus on like the stuff that will be new and using the integral in the context of this stuff. So we're going to look at mainly like 4 formulas, kind of like 2.5, because some of them are pretty close to the same. But some basic formulas and then just a few examples. I should be done with notes. My goal is to be done with notes like shortly after 3, save time to begin working on the homework today in class. So the first thing that I wanted to talk about is just some formulas that we have. Some of these formulas are going to be familiar to you, especially if you are in a physics class or have taken physics. And I guess my OneNote's frozen, so give me a second. There we go. And so the first formulas that I did want to look at was the distance, net distance, and total distance. So we have the net distance, and then we also have the total distance. We are asked to find these a lot. This is going to kind of basically where the first fundamental theory of calculus in many ways applies for these PVA problems. Before I really just jump into these PVA problems, I do want to remind ourselves that we have like the position, we have the velocity, and then we have the acceleration. To move from position, velocity to acceleration, we're basically taking the derivative. So oftentimes we think of like the position as the original function, the velocity as the first derivative, and then acceleration as the second derivative. So then likewise, if I'm moving in reverse, that is where we're going to be taking the integral. And I think most of us kind of know that. We've talked about it before when we were solving antiderivatives with like the plus c. So the two things that we have are we're going to talk about the net distance and total distance first. When I say net distance and total distance, that's like talking about a position, like how far has something traveled. Those of you in physics, what we call net distance in calculus is often called displacement in a physics class. And in fact, I use displacement a lot. If you said displacement, that would be fine. Even if you put displacement on the AP exam, that would be fine as well. It would earn full credit. Total distance, on the other hand, I think it's just called distance in physics, but we're still going to kind of emphasize total distance as well for that one, because it does have a slightly different meaning. When I think of net distance, I kind of think of that as if you have a starting point and an ending point, and you travel all over the place. The net distance is basically how far away you are from where you started. So like that solid brown line would be like the net distance from point A to point B, kind of ignoring the entire route that you took. Whereas the total distance, if you have that point A and that point B, the total distance is the actual length of the path that you took to go from point A to point B. So you actually want to find the length of that path. How does this connect to stuff that we do in calculus? The net distance, and I like calling it the net distance because I think it connects it to what it's related to in calculus. And net distance is going to be directly related to the net area. How do we find net area? The net area is the integral from some starting point to some ending point, and we're going to use v of t dt. Why are we using v of t? I think it makes sense. If you integrate velocity, that's going to turn it into position. Think about how we think about those part B problems. The integral of a rate, velocity is in a rate, is going to give you an amount. How do we adjust that formula if we want to find the total distance? To adjust that formula and find the total distance, we are still going to be integrating velocity. But instead of just like regular velocity, we are going to be integrating the absolute value of velocity. And that's something that students often forget. They want to treat both of those as the same formula, but total distance is going to be the absolute value of the velocity. And there's different ways you find the absolute value. Like we're going to look at example today. We're just going to be simply looking at the graph. You can also get to the absolute value in the calculator if necessary. If you're using a calculator, it is under the math button, and you're going to scroll over to the number column, and it's going to be the first option that is ABS. And that's if like you had a function and you want to use a calculator, then that's going to access it. A lot of the PVA ones are going to be more graphical, and that's what the example I picked up today. So to find the absolute value, we'll just say we're just going to make it positive. So what's negative would then become positive. So the questions that I want to answer in terms of these problems, we're going to use the same graph throughout the day today. I'm not going to switch it up. And we're just going to be looking at this graph. I deleted the word problem just because it didn't really fit on here, and I didn't want to lose the meaning, but this is the graph of velocity. So this is the velocity graph. I'm going to refer as to the velocity graph above. So this little bug is traveling, and this is its velocity. Some first semester stuff we know, and for those of you at home, I'm going to kind of highlight this as I talk about it. We know that when velocity is positive, that is like a forwards motion. So it might be going up or to the right or just moving forwards. So if I'm looking at this graph, this bug is moving forwards first. So that's where it is moving forward. At 0, that's a brief moment of rest. And then velocity is negative, so this bug is moving backwards, still moving backwards, at rest, backwards, and back at rest. So that's how we kind of interpret those graphs first semester. We're going to kind of expand today and just talk about how can we use this integral calculus in terms of PVA when looking at, in this case, the velocity graph. So to go back and kind of answer the questions, we'll kind of compare them. The side by side I have in that next column is I want to be able to compare the net distance with the total distance. Again, just like with all of them, you do want to kind of show your setup and then the answer. The net distance from 0 to 5. Don't need an initial condition. I want to just talk about what's happening from 0 to 5. The net distance is going to be the integral from 0 to 5 of v of t dt. How am I going to compare that to the total distance from 0 to 5? Still going to have a starting point and an ending point. So we would be finding the integral from 0 to 5. But now that I want the total distance, that's going to be the absolute value of velocity with respect to dt. How do we find that integral? So if we had the actual equation of velocity, punch that into our calculator and then hit enter, shows the one today where we have a graph because we do know how to find a definite integral using a graph. The definite integral using a graph is just going to be the area underneath the curve. I'm going to zoom out a little bit to kind of fit it all on the screen. So if I want to find the area, then I'm going to say that the integral from 0 to 5 is literally the area from 0 to 5. So we can just go ahead and divide it up into shapes that we know. That first triangle, 1/2 base times height, that's going to be 2 times 2 is 4, divided by 2 is 2. This little rectangle has an area of 2. This triangle has an area of 1. This triangle is below the axis and ends up having an area of -1. Again, net distance for us is going to be the same thing as the net area. So what would be the net area? We have 2 plus 2 plus 1, and then -1 for that negative area, which gives you a net distance of, that's going to be 4. How does that compare when you find the total distance? The total distance is the absolute value of velocity. Well, what does absolute value mean? It just means to make everything positive. Well, that first region, everything is still positive, so we still have 2 plus 2 plus 1. But that last triangle is negative, but its absolute value is going to make it positive. So instead of having a -1 for that last region, absolute value makes it positive. All those add together, we have 2 plus 2 plus 1 plus 1 has a total distance of 6. I think it makes sense to most students that the total distance is going to be greater or equal to than the net distance, because the net distance it is just kind of looking at like how far you are from the starting point. So to kind of give you a visual, this bug basically went forwards by 5 and then backwards by 1. So the net distance we found was how far away it was from the starting point. Meanwhile, the total distance, what it's finding, it went forwards by 5 and then backwards by 1. But the total distance it ended up traveling was that 5 plus the 1 that it went backwards. And that's where that kind of 6 is coming from. So we have the net distance versus the total distance. Definitely want to make sure we know those words. And then the other vocabulary words that I want us to look at. The first one we discussed first semester, but we're going to look at it in a different context this semester. That's going to be average velocity. The other one we're looking at is going to be average speed, which is going to be something that is new. For the sake of the problem too, I don't know why I typed it in. I meant for this second one to be t is equal to 5, so it matched the problem above it. It's the same thing here, completely meant for that to be t is equal to 5, not the 15. So, what is average velocity? Let's think about what that means. So either you remember it from first semester or maybe you remember it from physics. How do you describe what average velocity is? It's the change in what or the change in time? Change in displacement or change in time. That's like the very physics definition of it. We're going to describe in calculus like what is average velocity? Average velocity is the change in position over the change in time. Well, what does that literally mean? Change in position is going to be like end position minus start position, change in time, end time minus start time. It's basically old school slope. So if I want to find the average velocity, I'm going to use the function x sub t for position. So it will be the change in position over the change in time. So I had x of 5 minus x of 0 over 5 minus 0. What's the issue with trying to find the average velocity with the information we've been provided with in this problem? We don't have the position, we only have the velocity. Well, one unique thing we have in calculus is we now know how to write position in some ways using velocity. So I'm still going to have this 5 over 0, like that is part of the average velocity formula. How can I get to velocity, or excuse me, let me try that again. How can I get to position using velocity? The integral. So I know I'm going to be integrating velocity. Well, I somehow want to get x of 5 minus x of 0. I know that when I integrate, I'm going to plug in the top number minus the bottom number. So if I make the top number 5 and the bottom number 0, then we literally can see that this integral, so what is the integral of v of t from 0 to 5? The integral of velocity is position. Plug in the top minus plugging in the bottom. So what I've highlighted in green, those two statements are exactly identical. So we don't have to know the position. We can just use the velocity. What was the integral from 0 to 5 of v of t? We found that above. That was 4. And then all over 5. So the average velocity, I didn't put units on this one, but the average velocity would be 4/5. Same thing for average speed. We can come up with a pretty easy formula for average speed. Those of you who had me last semester, or I know Ms. Kennedy showed you this as well, if you didn't have me, what did we define speed as in calculus? So it is, so you're thinking of when is speed increasing or decreasing, and that is when we compare acceleration and velocity. Speed just by itself is basically velocity without direction. So you don't care about whether it's moving forwards or backwards. So we're just going to define speed as the absolute value of velocity. Again, that's from first semester, but again, don't remember it, telling you it now. So what is going to be the average speed? You can kind of think about what the formula would look like. The average speed is literally going to be the integral from 0 to 5 of the absolute value of v of t dt over the 5 minus 0. And that's going to be the formula that we use. And then we already found that one. what was the absolute value of velocity is integral from 0 to 5, 6, and then over 5. So it's kind of weird, but we have different values when we're talking about the average velocity, which takes into consideration the direction, and then average speed, which really isn't going to consider the direction. I do like also making some connections with that formula with stuff that you have already learned. To me, calculus is like one of those things where like it builds on math you've already learned. Like sometimes it's just like math in different ways. Like for example, when we first learned the derivative, that's just slope, and you started talking about slopes in the 6th grade. Well, things like average velocity, you've technically been talking about since 4th grade, maybe. Definitely didn't see integral signs in the 4th grade. But you do know what an average is. What is an average, or how would you find an average normally? Add everything up, and then divide by the number of things. Well, looking at this integral formula, an integral literally tells you to add up a bunch of things. Like think about Riemann sums, that's where they come from. So literally that numerator that I have in green is you adding up all the possible velocities divided by 0 to 5 is like the length of time. So you're dividing it by the number of velocities there technically are. So it is still like an average. It's just like the fancy calculus version of average, not the 4th grade normal math version of average. So calculus, we're just kind of building on stuff that we know. Any questions on that slide? All right, second slide, I just have 2 questions on, same graph. This slide is going to connect a little bit closer to some of that stuff we were doing the past 2 days. So I left it at the same graph, that is the velocity graph. I am providing us with this new piece of information. It says, suppose the bug begins when t is equal to 0 at x of 3. So basically we're saying that x of 0 is equal to 3. What type of information is that acting as? That's the initial condition. So we have an initial condition now. And we are asked to find the position at t is equal to 6. Notice this one is phrased a little bit differently. It's no longer like net distance. It's not asking to find the distance traveled from 0 to 6. I want to know where is this bug when t is equal to 6. This problem is basically like a rewritten version of the first FTC. So this is one where we would use the initial condition to basically solve it. So the way I think about this one, where is this bug starting at? This bug is starting at 3. Where did 3 happen at? 3 happened when t was equal to 0. What are we trying to find? We're trying to find where the bug is at when t is equal to 6. Well, which function would I want to integrate to talk about the distance or the location of it? I would have to integrate v of t dt. So it really is just like those problems we did yesterday. The initial condition plus the integral of a rate is going to give you the final amount. And then this becomes a pretty easy problem to solve. So I have the 3. How do I find the integral from 0 to 6? Well, that's just an integral. There's not an absolute value there, so we want to make sure that like area above is positive, area below is negative. We found some of these already. Like that was 2, 2, and 1, -1, and -2. So positive area of 5 minus a negative area of 3. Overall, this bug you get 5. Again, what have we basically found? We now know that x of 6 is equal to 5. Visually, I think some people, it helps them when we are talking about position and velocity acceleration, like it is a very visual thing. What we're basically saying is that this bug is starting at x is equal to 3. It moved forward by 5, and then it went back by 3. Where has it ended up at is now at the position of 5 because of kind of the backtracking that it's done. Or not more by 5, yeah, by 5. So then, next question, again, just kind of pulling together the pieces that we have. Suppose the bug begins, same initial condition, when t is equal to 0 at a position of x is equal to 3. I have at what other times will it be at x is equal to 3? I think sometimes people make this problem a lot more difficult than it reads. So like if I maybe put this in something that you might understand, like let's talk about what's happening today. This morning you woke up at your house. Some of you are still at your house, but some of you came to school. And then you're going to go back home eventually. Well, if you're at home, come to school, but then end up back at home, technically what's your net displacement for the entire day? 0. Like you ended up back where you started, your net distance is 0. Your total distance is not, but your net distance is 0. And that's kind of like what this problem is asking you. This bug is starting at 3, it's traveling around. We want to see when it ends up back at 3. So we are going to be basically looking for when the net distance is equal to 0. Well, what is the net distance represented by? The net distance is represented by an integral. So we're basically going to be looking for when an integral is equal to 0. Some students like having an equation for this, so I am going to give you an equation, though I think it's very doable to solve this one without an equation. The bug is starting at 3. It starts at 3 when t is equal to 0. We're trying to find a time, so I'm just going to put a question mark there, that after it travels for some amount of time, it ends back up at 3. So it starts at 3, we want to see where it lands at some point at 3. Well, subtracting 3 from both sides, we're basically trying to find when this integral is equal to 0. What would it mean for the integral to be equal to 0? What would that look like on the graph? The area, and what would it mean if the area ends up being 0? Same on top as the same on the bottom. So basically all that positive area has to cancel out with all of the negative area that you see. I'm going to scroll back this problem in case you're still writing it, but let's go ahead and look back at the graph. So the only positive area I have is this positive 5. Which basically means like the bug has moved forward by 5. So once I see negative 5, that means that like all that walking forward the bug did is going to be canceled back out. So I already found area of -1, area of -2, one more kind of block over. There it is. There's the area of -5. So again, basically what that means, the bug walked forward by 5, back by 5, it's right back where it started. So that will be one place where it's back at 3. Looking at this graph, what do we need to worry about if it's going to hit 3 any other time beyond the 7? No, if you're looking at it, we have negative area walking backwards, negative area walking backwards. There's not going to be another chance for that area to cancel out. So there's no point in checking to see if there's any more because we know there can't be another place. So at what time did it end back up at 3? That was a time t is equal to 7. How did we know? Because that's where the integral would be equal to 0. And that integral itself represents the net distance. Yes, Hermione?
For that one, with the 7, you guys will go to the top of it.
Yeah, so that would be if I wanted to complete it. Basically, this top part of the integral is the 7. And 3 plus the integral from 0 to 7 equals 3, meaning we're back where we started. Or you can think of it as the integral from 0 to 7 is 0. So yes, we could have walked all over the place, but we have a net distance of 0.
So your t never goes back in that like middle.
Yeah, the time when we do these problems, even for the part B, we're always going to put the time kind of on the integral sign when we're talking about like an amount. And even whenever you write an integral sign, we're always going to plug it on the integral sign and not inside it, like not in where the v of t is on the problem. All right, one more problem to do. And this is where I'm going to stop at today. I know you see 2 problems here, but I really just want to do that first one. We have kind of alluded to absolute extrema a lot. I know some of you are new to me, so that's kind of one reason why I've included a lot of them, just to make sure we know how to find these absolute extrema. Also, hopefully it's a big enough hint to you that you probably, definitely, yes, for sure, have an absolute extrema question on your quiz on Monday. So let's just review it one more time. We wrote this down yesterday. But how do we find absolute extrema? For absolute extrema, you're basically making a t-chart. And on that t-chart, you have to look for two special types of x values. You're always going to include your endpoints, and you're always going to include your critical points. How do we find critical points? That's where the derivative is equal to 0 or where the derivative is undefined. Once you find those points, put that in kind of the x column, plug it into the original function, look for the highest one if it's a maximum, look for the lowest one if it's a minimum. How this changes for a PVA problem, not much. For a PVA problem, instead of x's, we tend to use t, because we're talking about time. And we know we're going to be doing a Candace test when we see things like find the closest or furthest away. So kind of like those extremes, that's your clue that you're going to be finding the absolute minimum or absolute maximum. Well, if I'm talking about something being the closest or furthest from me, we're talking about like the position that it's located at. So instead of like the y, we're going to be looking for the position. What numbers still go on your Candace test? The endpoints will still go on your Candace test. And the critical points still go on your Candace test as well. We know the critical points can be found in different ways. Yes, that is true when the derivative is equal to 0. For those problems yesterday, it ended up being where like the rate in was equal to the rate out. I think those are kind of like the complicated ones to deal with. For PVA problems, it kind of looks more like that first one. What's the equivalent to y prime when we're talking about position, velocity, acceleration? Velocity. So the critical points for this problem is going to be when the velocity is equal to 0. And that's going to be the main thing we want to find to go on our critical points for here. So the question I have, I left it with that same initial condition. Suppose the bug is beginning again, t is equal to 0, x is equal to 3. What is the furthest right the bug is going to get? So I'm looking for like the furthest right. So I know this is going to be talking about a candidate test. So again, I'm going to go ahead and draw it. I know that I'm going to have a t, and I'm looking for the maximum position, specifically the maximum like positive position, the furthest to the right. And then I want to go ahead and fill in my x values and then use that to find the position. So the first thing that we know is we are going to include our endpoints. Looking at the information provided, where is this graph starting at and where is it ending at? 0 and 15. So we're going to include 0 and 15. And then we also want to have the critical points. The critical points is when the velocity is equal to 0. Well, we're looking at the velocity graph. So literally when it's equal to 0 is going to be when it's located where? On the x-axis, when it changes signs from positive to negative. So I have a critical point here. That would be at 4. And I have another critical point here. That is at 11. One of those x values or t values I highlighted is going to be when the bug is furthest to the right. So I'm going to go ahead and add that to my Candace test. That was 0, 4, 11, and 15. If you show something like that on your quiz, that's already partial credit. You considered the endpoints and you considered the critical points. One of those rows is really easy to fill in. Which row do we automatically already know the answer to? The first one, right? When at t is equal to 0, what's the position? The position is 3. Again, that could end up being the furthest right we are, but it could also be at the 4, the 11, and the 15. So now here's where like the tedious part, the integrals come into play. What is the position at 4? The position at 4 is this bug starts at 3. That 3 happened at 0, traveling to 4, of v of t dt, and we're going to use the graph to find that. Where's the bug at 11? Again, it's starting at 3, starting from 0 to 11, v of t dt. That will be the position of the bug at 11. How can we find the position of the bug at 15? That will be 3 plus the integral from 0 to 15 of v of t dt. Now, this was one that we could use our calculator had a function. Again, that's just a bunch of like type in your calculator and then enter. For this one, we do need to go ahead and worry about the graph. Again, how do we find an integral? We're going to find the area to determine that integral. So we had 3 for that first one. From 4, so I'm going to find that one. Already did this one. That was an area of 2, 2, and 1. I know that the integral from 0 to 4 is 5. So answering that row, it started at 3, went 5 more, and now it's at 8. Can be lazy and use my previous answer to help me answer the next row. So like at 11, we're starting at 8, and then we want to see how much further it's gone up until 11. So if I'm going from basically 4 to 11, dividing it up into shapes, that's an area of -1, -4, and then that's a triangle. What's that? 2 times 4 is 8, 1/2 of that, -4. So from 4 to 11, it's gone -9 more. We left off at 8, so then minus the 9. This bug is now located at -1, and then we can kind of finish it out for the last row. Where did the bug end up at? Last triangle is also below the x-axis. It has an area of 1/2, 4 times 2, which is also -4. So then that last one, it went -4 more, and is -5. So the answer to the question, what is the furthest right the bug is? So the furthest right against is 8. So the furthest right is 8. And that does occur at t is equal to 4. Well, if I change the question and said what was the furthest to the left it got, and what would be your answer for that one? -5, and that occurs at the 15. You would have to do a candidates test to justify your answer. Like in calculus, you have to have a candidates test when you are justifying an extrema. I do think looking at the graph, it seems obvious that that really is going to be the maximum. Because at 4, that's the last place that bug stops moving forwards. Everywhere else it's negative, so it's just always moving backwards. So that really was logically the only possible answer. But how we justify that in calculus, mainly to make College Board happy, is doing a candidates test to show that we have considered all the possibilities. Questions on that? All right, so that is where I'm going to go ahead and stop today's notes at. What I want you working on for the remainder of class and then have ready for tomorrow. At this point, you can do all of homework 2, part A, part B, and part C. Tomorrow is going to be just a work day. Like I don't have any notes planned. I'm not going to do any notes. I just want you to work and basically come with a whole lot of questions to ask. If you're the type of person and you just don't want to ask questions, you're like, Mr. Brown, just give me a bunch of practice problems to do. I do have some practice problems shared with you in OneNote. So if you're looking immediately after the notes, you have this first one, optional practice. The key to this is posted online, but it's just a mixture of problems to practice. I have first FTC and second FTC stuff. I have another slide, more practice, again, all optional, just like seeing problems. Some students like this second one because I have some problems that are already worked out. Especially if you have like a hard time coming up with justifications. So like I'll have like one problem and like, here's some bad justifications and then some good ones, just in case you have trouble kind of forming those. But again, all I want you to focus on right now is getting that homework done. You need to have the practice with this stuff, and then showing up to class tomorrow with a bunch of questions. So other than that, yeah, I have nothing else to add. I will let y'all go ahead and get started on that.
So are both homeworks due on Monday?
Both homeworks, except for homework 0, but both homeworks, yeah, should be done on Monday for the class.